Good afternoon, sir.
Good afternoon. Good afternoon. Dr. Rajesh, yes, good afternoon. Madam, Madam.
Good afternoon, Dr. Pastor. Yeah, I'm here.
Yeah, good afternoon, madam. Good afternoon. Good afternoon, ma'am. Good afternoon.
Good afternoon.
Good afternoon.
Nice meeting you.
Nice meeting you, ma'am.
So everyone in India is working from home now?
Oh, yeah.
Okay, same as here.
Okay. Actually, in 10 minutes people will be joining, madam. I'll just remind them. Actually, they are in another track. Actually, they are in another track. Has got delayed. The inauguration has got delayed and extended for 10 minutes. So,
I see.
as a ripple effect, it has. We may take 10 more minutes.
No problem. We shall wait.
Good afternoon, sir. Good afternoon. I'm Devasaya Chemistry. Welcome.
Good afternoon.
Welcome, madam. Happy to
Thank you.
thank you for this today's program. So I will request chemical HOD also to join HOD chemical engineer Dr. Mayappan. Just I will call him.
Okay, sure.
Madam, can you share a few words about your current area of research?
Okay, sure. Let me give the.
Till others are joining, we'll like to.
Okay, sure. Basically, I'm from the Fuel Cell Institute in the University Kebangsaan Malaysia. So, in this institute, we are actually focusing on the research related to the fuel cell components. Actually, it's from the research we focus on from the hydrogen production to the utilization. That means from production to the utilization of hydrogen in fuel cell itself. So our main research focus is actually on the catalyst development as well as the membrane development in these hydrogen fuel cells. Yeah. So we have quite a number of groups in our research center. So each of the group have different focuses. They, for instance, there are groups which focus on different types of fuel cells. Okay, so we have in my group itself, it's on hydrogen fuel cell. There's other groups on the direct liquid fuel cell. There's some on microbial fuel cell. Then we have also the groups on the photoelectrochemical cell. That's for the water splitting. Okay, and also there's a system development, the whole fuel cell system development, as well as the electrolyzer development. Yeah, these are our main research area.
So, whatever the catalyst you are preparing, that is used for fuel cell application.
Yeah, right. We are very focused in our research. We prepare the catalyst based on the applications in fuel cells itself.
So, what is the name of the catalyst? Just now you have mentioned that.
Okay, so basically, if we look into the development, the research in this area, we are looking for these low cost kind of catalyst to replace the platinum. So we are looking into this transition metal based catalyst. Yeah, that's our main focus. Then what we are actually studying is on the structure, the morphology, the use of the type of precursors used, and how it affects the activity, the catalytic activity, as well as the catalyst support material as a whole. Yeah, how that synergistic effect occurs that will affect the catalytic activity.
So whether the catalyst is environment friendly?
Yeah. For the time being, if we are talking about the synthesis process, we don't consider it as an environmentally friendly process, but it's more on in overall when we put this in use in a fuel cell, the whole fuel cell system, which uses hydrogen as a fuel to generate the electricity, is a green process, which means to say when we generate electricity, there is no carbon emission, there's no carbon footprint. But more on, for this type of fuel cells, we only produce water as the products and also heat. Yeah, that's the idea of it.
So how would the catalyst characterization, what are the techniques you are normally using, you use for this characterization? And
Okay.
what parameters you are studying under characterization?
Normally, we focusing on the electrochemical characterizations technique on the catalyst that we produce. Then it will be supported by. Then we will study the correlationship between this electrochemical behavior of the catalyst with the physical chemical behavior characteristics. So we actually mainly these electrochemical characterizations we're using this potential stat, where the main technique that we use is the rotating ring disk electrode. Yeah. So that is to study the activity, the electrochemical activity of the catalyst itself. And also, of course, it couples with several other techniques such as cyclic voltammetry, chronoamperometry technique, and also the accelerated durability study. Yeah, that are the few main techniques. And of course, in addition, we have to study on the physical characterization and chemical characterizations that we use standard instruments like the SEM analysis. Then we have the X-ray photoelectron spectroscopy (XPS). Okay. Then we also study on the surface area, the PET surface area. Yeah, and also that is part of it.
Thank you. So one of our colleagues is also in fuel cell area. So I think he will join and he may clarify some of the points with you.
Oh, sure, no problem.
Dr.
It's good to have a
Namaste,
discussion.
just I will call him. He will also join with us.
All right.
Anand, any questions with respect to the catalysts which are used, because you are specialized in nanomaterials? Just anything you can clarify with the madam.
Sir, we have to start the program on time, sir.
Like for you join from HOD chemical.
And already we are going behind the schedule. நம்மளுக்கு
இருங்க இது பரத் சார் ஜாயின் பண்ணாரு. நான் கால் பண்றேன் கெமிக்கல். பாஸ்கர் ஒரு கெமிக்கல் வச்சோடி பேசுனீங்களா? நீங்க கெமிக்கல் வச்சோடி இது பண்ணுங்க, நான் மேட்ச் பண்ணுவேன். சரி சரி அவங்க இதுல இப்போ செஷன் இல்லாதவங்க இங்க நமக்கு இது கூப்பிட்டுங்க, அது இதுக்கு வந்து இது இருக்கட்டும், நான் மேட்ச் பண்ண உள்ள வர சொல்றேன். ட்ராக்ல நம்ம மக்கள் இப்போ இது இல்லாதவங்க கூப்பிட்டுங்க, இதுக்கு அங்க மொத்தம் இருக்கட்டும், இங்க இதுக்கு வர சொல்லிடுங்க. நம்ம இது நான் இதை மேட்ச் பண்ண மாட்டேன். Stanley, 1 minute, I will call Archer.
இல்ல சார், எனக்கு ஒண்ணும் இல்ல சார். நோ ப்ராப்ளம் சார். நம்ம டைமுக்கு ஆரம்பிச்சிட்டா சரியா இருக்கும்னு பார்த்தேன்.
மேட்ச் பண்ணி இந்த காமன் மீட்டிங் லிங்க்கு வாங்க. ஃபியூயல் செல் அந்த கீனோட் அட்ரஸ் வெயிட்டிங் மேடம் வந்துடுங்க. ஹெல்ப் பண்ணி மீட்டிங் காமன் மீட்டிங் லிங்க்கு வந்துடுங்க. ஃபியூயல் செல் ஏரியா ரிலேட்டட் ஒர்க் ஆரம்பிக்க போகுது. ஸோ ஸ்டார்டிங் ஜாயின். ஸ்டான்லி வி கேன் ஸ்டார்ட். இப்போ யார் இன்ட்ரோடக்ஷன்? யார் இன்ட்ரோ? Bhaskar? Bhaskar sir?
Yes sir. Sir, good afternoon. Sir, நீங்க எந்த பாஸ்கர் சொல்றீங்க சார்? விவசாயம் சார், எந்த பாஸ்கர் சொல்றீங்க? Sir?
HOD sir, HOD IP sir, welcome sir. HOD physics, welcome.
Welcome sir, welcome.
Bhaskar, இப்போ intro யார் இப்போ?
சொல்லியாச்சு sir. Now Anusha, you can start the program.
Okay, fine.
A very good afternoon to everyone. I'd like to extend a warm welcome to you all for the online international conference on green materials and renewable energy. Now, I'd like to call upon Dr. G. Saraswati, Associate Professor, Chemical Engineering Department, SVCE, to introduce the chief guest.
Thank you, Anusha. I'm very happy to introduce and welcome Dr. Wang Wai-in, Research Fellow, Fuel Cell Institute, University Kebangshan, Malaysia. Dr. Wang Wai-in completed her PhD in Fuel Cell Engineering, specializing in the area of Fuel Cell Electrocatalyst in 2014. She has led several national and university research projects as well as being active project members in industrial projects related to hydrogen and fuel cell technology development. Dr. Wang was also the editor of technical code on hydrogen storage and safety with fuel cell as power generator for information, communications and technology infrastructure, and currently serves as the committee member of technical code drafting on development of stationary fuel cell as a backup power solution for the telecommunication sites. She is also the member of the Malaysian Association of Hydrogen Energy, which is established in 2017. So I once again welcome you, ma'am, and the title for her speech is Hydrogen Fuel Cells as Clean Energy Generation Devices in Development in Catalysis. Thank you.
Thank you very much for the kind introduction. Okay, I'm now sharing my screen. I hope that everyone can see my screen, my slide.
Yes, ma'am.
Okay, thank you very much. Let me start with the presentation now, since I can see that we are quite behind of time. Right. So the title of my speech today is on the hydrogen fuel cells as clean energy generation device, and the focus topics in this session is on the development in catalysts. So let me first start with the introduction of fuel cells, since not everyone of the audience here could probably know about fuel cells. Okay, so fuel cell is basically an electrochemical device that converts chemical energy from a fuel, for example, hydrogen, to electricity. And this electrochemical process that occurs through the redox reactions to generate electricity. As we can see from this schematic diagram, a typical schematic diagram for fuel cells, it is made of a membrane, a solid electrolyte membrane, and established with a two-layer of electrodes. On the left-hand side is the anode, and on the right-hand side is the cathode. So on the left-hand side, the hydrogen is fed to the electrodes, the anode, where this hydrogen oxidation occurs, and that produces the hydrogen ions, or we call as the proton, and that will generate the electrons that will travel through the cathode. Okay. So these hydrogen ions will travel through this membrane and then to the cathode, where the oxygen coming from the air will combine with the proton and the electrons and undergoes the oxygen reduction reactions to produce water. As you can see from these reactions, water is the only product from the process, and the electricity is generated from this process through a electron transfer process. And the uniqueness of this fuel cell technology is that the fuel cells can produce electricity continuously for as long as fuel and oxygen are supplied. It is just like our petrol vehicle. As long as petrol is supplied to the vehicle, the engine is being powered. When the petrol is depleted, then the engine is not able to move. Similar concepts apply here. So if you look into the fuel cell market, interestingly, if you look into worldwide, you can see that in this region, the Asia-Pacific region shows the highest growth rate, okay, among all the countries in the world. The main three key players in contributing to the fuel cell markets are the China, Japan, and South Korea. These three countries, they are mainly driven by the government federal policy towards the low carbon economy, and also with the attempts to cut the environmental pollution and greenhouse gases emission. And when we compare these three countries on the aspect of the national fuel cell electric vehicle target numbers, we can see that China is progressing very well in terms of the numbers with time, with years. This is again due to, as we know that in China, there's a severe pollution issue, and the government is working aggressively towards improving the air quality through investing in the green technologies that will cut down pollution. And China now is actively working on developing the hydrogen vehicles manufacturing. So these three countries did have some demonstration initiatives that has been performed in their respective countries on several huge projects. For example, in China itself, we can see that for the 2022 Winter Olympics in Beijing, they're actually planning to deploy the fuel cell electric buses. They're planning to deploy about 74 buses from the Zhangjiakou city to transport the athletes, okay, for the Olympic Games. So all these vehicles are being manufactured locally by them with their home technology. Well, if you look into Japan itself, Japan was among the earliest countries that has they have aggressively worked on commercializing the fuel cell system. They started this farm program in 2015 until now. This is actually a program that's focusing on the residential area. They actually sell the units, this residential micro combined heat and power fuel cell system unit, this unit to the household. And from 2015, they actually sell about 120,000 units. And then in 2018 itself, they actually sell about 50,000 units, which is equivalent to 350 megawatt power itself. So this will be installed in every every household. And the unique features about this is that they're actually using town gas as a fuel source to power the fuel cell. And in this process, in this system itself, there are two main unit operations involved. First is the fuel processing system, where the town gas, which mainly consists of the methane gas, will be converted into hydrogen through the internal steam reforming process, and this hydrogen will be directly fed to this is the fuel cell unit, photon electrolyte fuel cell unit. Okay, so from here, the direct current electricity will be produced, okay, and also together with heat. The whole process itself, the energy source, the fuel, will be converted into electricity with an efficiency of about 35%, and the remaining, about 35 to 40%, it's converted into the form of heat. So this made the total efficiency, energy efficiency, to be 80%, which is relatively high. Yeah, and the water, the heat can be used to heat up the water in the household, while the electricity can be used to power the electrical appliances in the household without the need of using the grid. Okay. So there's another initiative done in the Tokyo in Japan, which is this 2020 Olympic and Paralympic Games in Tokyo. Yeah, unfortunately, due to the pandemic, these games has not been started yet. But the initial plan was that they are planning to use the hydrogen-based fuel cell technology to power several operations in the games. Okay, so among which the Toyota, as the very well-known automobile company in Japan, is actually one of the most active player in producing these fuel cell vehicles. Is planning to sell about 100 units of fuel cell buses to this Olympic Games, and also the government has allocated a huge sum of money to support the use of hydrogen fuel cell technology in these games. However, if we have these fuel cell buses or fuel cell vehicles produced, we need the infrastructure. We need the infrastructure in order for it to be able to go on road, right? So the plan is that to use these Olympic Games as the starting point to build this hydrogen town. So we need the infrastructure. If we have the fuel cell, we have the car, but we do not have the fuel, the car is not going to move. So we need this hydrogen refilling station available in the town where there is this fuel cell vehicles. So the idea is that the Olympic Game Elites Village will be equipped with all the infrastructure and facilities related to hydrogen. Okay, so the hydrogen pipelines will be built in the town itself, including its connection to the hydrogen refilling station. Okay, and also the hydrogen can be used to power the facilities within the township. Okay, for example, the commercial facilities and the schools, they can use a fuel cell system to power the facilities, the utilities, instead of using the grid power. Then if looking at the South Korea, they have this world's largest industrial hydrogen fuel cell power plant. Okay, this is just completed in 2020, very recent, just 1 year ago. And but until now, they're still using the hydrogen recycled from the petrochemical manufacturing. As I mentioned just now, the hydrogen in the Farm program in Japan, they're actually using the town gas, the methane gas. As long as you are using the hydrocarbon gas to convert it into a hydrogen, we don't consider it as green hydrogen. So in this process, even though we say fuel cell is a green device, green energy generation device, but without the green process at the front producing the hydrogen, the whole process we don't say that it's 100% clean. So how to achieve this green hydrogen production? The key here is not to use the fuel from the petrochemical industry. So I will talk about that later. Okay. Now I would like to move on to the advantages of what are the advantages of fuel cell technology after I have discussed so long. First, by converting the chemical potential energy directly into electrical energy, the fuel cells can avoid the thermal bottleneck, which is a consequence of the second law of thermodynamics, and it is more efficient than the combustion engine, which first they have to convert the chemical potential energy into heat and then turns into the mechanical work. And second, the direct emissions from a fuel cell vehicles are just water and a little heat. So for sure, this will cut down the greenhouse gases emissions in total. Third, fuel cells have no moving parts. So when there's no moving parts, that means there's minimum maintenance needed. There's no maintenance on ensuring adding the lubricant to the mechanical parts like the combustion engine. So we can say that it's more reliable than the traditional engines. And lastly, the key is that hydrogen can be produced in an environmental friendly manner, while oil extraction and refining is very damaging. So now, how to produce hydrogen through an environmental friendly manner? The key is to use the renewable energy mix in order to supply this energy source to form the hydrogen in this process. This process is actually a very conventional process. We call it as a water electrolysis process. Water electrolysis process is an energy intensive process. It needs a lot of energy. But if you imagine that we are using the energy from the grid, if that energy from the grid comes from the petrochemical, okay, there's still carbon footprint. So the only way is that we have to use a renewable energy source to power this electrolysis process. With this process is green and this process is green. And then the hydrogen produced will be green hydrogen. And hydrogen can be used not only for fuel cells, also for other applications. Okay, but the focus here today is still on fuel cells. If you look into the components in a fuel cell device, as I showed in the very first introduction, we see a schematic of these three layers, the membrane and the two electrodes on the left and right. These three layers, they are the core component in the fuel cell responsible for the electrochemical reactions. Okay, these three we call, when we hot press them together like a sandwich, we call them as membrane electroassembly, MEA. Okay, but with only these three layers, it's not going to function. So we have to actually stack it in like a battery form in order for it to work, because we need to fit in the fuel, how the fuel hydrogen is going to fit into the system. So there should be a proper components that is responsible for the fuel management, the water management, even the heat and the pressure management. So these are the components that's used to design to complete the set. First, the outer layer is actually this bipolar plate. This bipolar plate consists of this flow field, where the gas will flow through the channel and then it will diffuse through this gas diffusion layer in gray. And this gas will slowly diffuse into the catalyst layer in black, and then undergoes the reactions and the process occurs, the electrochemical process occurs. Okay, so basically now when we talk about fuel cell is an energy generation device, definitely we are desired to design it to cater for a certain power criteria, right? So how do we actually do the design? How do we consider design? It's a very simple physics formula lying behind, which is power equals to potential multiplied with current. Okay, so now we're just going to play with how we design the stack based on the potential produced and the power and the current produced. Okay, imagine that this single stack, okay, this is MEA with a plate. So one single cell is cell 1, cell 2, cell 3. Example. Imagine that one single cell is a battery. If we connect the batteries in parallel, we know that when we connect the batteries in parallel, if one battery has 1 volt, 3 batteries in parallel give us 3 volts. The same concepts apply for fuel cells. Now, if we stack these cells in parallel together, considering one single cell has true potential voltage, 2 cell potential to be 0.7 volt, if I stack 100 cells together, I will get 70 volts. Now, in order for me to obtain the required power, for example, 2.24 kilowatt, I need to design the cell area, the size of this stack. Typically, a single cell MEA, it can produce about 0.8 ampere per cm square of the current density. So now I can just simply think about how big the size that I want. Okay, so say 20 times 20 cm square. This will give us 400 cm square, and multiply with the current density, that will give us 32. With this multiply out, that gives us the total power with these 100 cells and 400 cm square active area in a single stack. Okay, that is a very compact single stack which can give us this amount of power. So it's very robust for fuel cell design. It depends on the power requirement, how many stacks we are going to stack on, And also we consider the space. We want to have a long or a tall unit. Okay, it depends on the space requirement or yeah. And in terms of the R&D, because by far in the market, we don't see many of these fuel cell technologies has been commercialized and been marketed. Not even in Malaysia actually. Yeah, the main reason is that fuel cells is too expensive. Not everyone is affordable. Except that, for example, the countries, they're actually giving out the subsidies to these people, so they can absorb some costs. Okay, so I can give you an idea about the cost of these fuel cells. This is a fuel cell vehicle compared with the conventional engine vehicles. The price of these fuel cell vehicles is about 10 times the price of the conventional engine vehicles. 10 times, that's a huge cost. So why is this fuel cell so expensive? The key is because of the materials itself. In the fuel cell, as I mentioned just now, the catalyst itself, they're actually using platinum. Platinum is very expensive. They use platinum as the catalyst for the cathode and anode. And this electrocatalyst itself has already summed up about 30 to 40% of the overall manufacturing cost of one single stack of fuel cell. Okay, and not to mention about other components which are also expensive, such as the membrane and also the bipolar plate. Hence, the research and development related to fuel cell is actually aimed at reducing the cost through materials development, either by reducing the amount of the platinum used or totally replaced it. Okay, and also for other components as well. And at the same time, when we're trying to search for alternative materials to reduce the cost, we also have to look into the efficiency and the durability of the materials itself. So the research in fuel cells, once the materials are developed, the next step can help in the achieving these goals are the process system design as well as the system optimizations. So this is actually a multidisciplinary subject in terms of research and development. Okay, so now let's move on to the development in catalyst itself. In catalyst itself, as mentioned, we have anode and cathode. For anode itself, there's less study as compared to cathode because anode, where hydrogen oxidation occurs, platinum is the ultimate catalyst which has the best performance. There's not much can be done except that trying to reduce the amount of platinum while maintaining the efficiency and so. But on the cathode side, they are more focused, there are more research on it, simply because of even if we use a platinum as the catalyst, the overall potential, that means the efficiency on catalyzing this ORR is still low. It's still far lower than the anode. The overall potential is about 300 millivolt. Okay, so that trigger the researchers to look for alternative materials. Since platinum itself gives a high overall potential, why not search for other alternative materials as well? So the development comes into different areas. First is the precious metal catalyst, as mentioned, the platinum and also palladium as part of the precious metal catalyst. So on this regard, trying to reduce the loading is one of the approach, and also the trying to improve the lifespan of the catalyst is another approach that's being progressed. Secondly, on the non-precious metal catalyst, this is a main key focus that most researchers are studying, mainly on searching for non-platinum catalysts. To date, the most active catalyst that has been investigated is the iron and cobalt with nitrogen doped carbon catalyst. These have been extensively studied, although they have not achieved what the performance as the platinum, but they are in good progress. Okay. Then next, there's also study on the metal-free catalyst, but this metal-free catalyst, they use no metal, but they're actually using heteroatom doping on the carbon itself. For example, nitrogen doped carbon, boron doped carbon, sulfur doped carbon. With this, they actually create the active sites for the oxygen reduction reactions. However, this catalyst is found not suitable to be used in hydrogen fuel cell, but is more suitable to be used in alkaline fuel cell itself. And because when we talk about the non-precious metal catalyst, we find until today the active sites. Where is the active sites for this catalyst is still ambiguous. We're still speculating. So there's also attempts on studying on single atom catalyst to examine the actual active sites of the catalyst itself. Okay, so these are a few main areas that we are looking into for oxygen reduction reactions catalysts. And on the right side, these are the works that we have done in our lab. This is the list of the development of non-platinum electrocatalysts in our laboratory. In the beginning, we studied purely on the nitrogen doped carbon nanotube without metal. It's a metal-free catalyst. As mentioned, the results not promising. And then slowly we move on to the cobalt and iron-based, and also we look into the metal organic framework catalyst, which is very promising at the moment. And also one thing to highlight is that we are also looking into the use of a carbon nanostructure as a catalyst support material, because we need, as an electrocatalyst for fuel cell, we need these catalysts, for example, the metal, to be supported on a carbon surface, because as mentioned just now, if you have these electrochemical reactions occurs during the oxidation, the electrons is produced. Then these electrons has to use the faster routes to travel out to the external circuit. So carbon is a highly conductive, electrical conductive material. So we are using carbon as the carbon support in order to facilitate the electron transfer. And why carbon nanostructure is simply because if conventionally we are using carbon black or Vulcan carbon, which are amorphous in nature, and during a long-term operation, these carbon corrosion issues occurs. So with amorphous structure, it's easier to be corroded, to be dissolved. Dissolution process takes place. But if we use a carbon nanostructure, the graphitic level is higher, the graphitic degree is higher, so it can reduce tendency of this carbon dissolution issue. Hence, the attempts that we have made earlier was on the carbon nanotube, and later on when the graphene is in a hot pursuit, then we change it to the use of the graphene, or in another form, reduced graphene oxide. Okay, so in this the next slide, what I'm going to discuss is actually on this particular work. We are using this iron nitrogen doped carbon as the catalyst, and it supports on the reduced graphene oxides derived from the biomass itself. Okay, these are the recent works that have been published, and the student has just passed YY early of this year. Okay, so the idea of this project comes from the students. She was from Indonesia. She looks into the different type of biomass. For example, for instance, for this is the sandalwood. Sandalwood itself, it is used to make a money paper in Indonesia. Okay, so this is sandalwood, and on the nature in nature form, it's the structure of this sandalwood is in a honeycomb structure. Okay, and we found that if it's a honeycomb structure, it could be suitable through a series of process to be able to exfoliate into a nanosheets with high porous, high surface area. Okay, so that's the idea. And also we want a highly graphitic structure to be used as a support materials. And also what we are looking into is that we know that biomass consists of a lot of impurities, impurities in it. But these impurities may not be good because it creates a defect site. For certain applications such as supercapacitor, it needs a very smooth flow of electrons. But for fuel cell applications, it's different because when used as a catalyst support, we need more defective site in order to anchor the catalyst particles on the surface. Okay, so this will provide more defect sites that allows the anchorage of the catalyst particles. Secondly, we look into the impurities of this biomass, which we know plants consist of the compound of nitrogen compound and the sulfur compound. So all these, as mentioned, if we use it as a metal-free catalyst, right, they have some activities, they have some intrinsic activities related to OR activity. So it could also contribute maybe little to the overall performance. Okay, so that's the idea. And how we did it? by far, the synthesis of reduced graphene oxide from the biomass, they normally use this base activation method. They're using a KOH base activation method. So in this one, we are looking at other options where there have not been any attempts on using Hammer's method that's normally used to prepare the reduced graphene oxide from graphite. So there have not been any attempts on biomass yet. So we are attempting on this method, and hence what we did is the biomass was first carbonized using a hydrothermal method and then microwave it to produce a carbon powder. They actually put it in the microwave, and then this it will undergo this Hammer's method to the intention is to create a more defective sites on the layers in the carbon in the biomass itself. So we create the oxygen, the functional groups. Okay, it's basically oxidation. Okay, we oxidize it so that try to create and exfoliate the layers. Then we undergo the pyrolysis of this material under inert environment. So from this process, the volatiles will be removed, and also all the oxides will be reduced. Okay, so that will create reduced graphene oxide. And in this method, we attempted to use a different pyrolysis temperature from 700 to 900 degrees Celsius. Next, following, we'll select the best RGO prepared and use it for the FEN RGO catalyst preparation. We call it as a FEN RGO because we produce this catalyst with the RGO in one pot. Basically, what we do is we use an iron salt and also the nitrogen precursors that we show in the next slide. And this is a graphene oxide, not RGO. It's a graphene oxide. That's a product from here. Okay. Since this process, the pyrolysis process are the same, so the product from here will directly mix with the iron oxide and also the nitrogen precursors and subject to the pyrolysis. So we attempt on 2 steps pyrolysis in order to examine the difference between the first step pyrolysis and the second step pyrolysis in terms of the OR activity and also the morphology. This is the micrograph of the RGO produced from the biomass at different temperatures. As you can see from here, from 700 to 900 degrees Celsius, we can see that at 900 degrees Celsius, you can see the morphology is less dense and they are thinner in layer. That means they have been more successfully been exfoliated from the bulk structure itself. Then we look into the TEM image. You can see that it's a sheet-like structure, and also the SAED analysis shows that it's a polycrystalline structure, indicating that the graphene, the reduced graphene oxide that we obtain, is actually in the form of few layers RGO, not a single layer RGO. Okay, and interestingly, we can see this. The BET surface area for this RGO 900 is higher than that prepared in-house by using the graphite. Okay. To further confirm the success formation of the RGO from the biomass, we perform the Raman and X-ray diffraction analysis. Can be seen from this Raman analysis, the peak are similar to the RGO from graphite, but with temperature increase, you can see that the ID to IG peak increase, indicating that the defective site, the defective intensity, intensity in the RGO 900 is higher than 800 and than 700, simply because at 900 degrees Celsius, at high temperature, more volatiles have been removed, and that leave the defective sites on the surface. Okay, and similarly, we can see that XRD shows very similar patterns compared to the RGO. So these informations have verified the formation of the RGO from the biomass itself. Then we select the RGO 900 for the further study as the catalyst support itself. So the 4 precursors that we use in these studies consist of the urea, ammonia, choline chloride, and polyaniline. Okay, and we added with the Fe salt, iron salt. We can see that the first pyrolysis has produced the samples with coarse and dense structure, indicating the agglomeration of the catalyst particles. But upon the second step pyrolysis, we can see the less dense structure is formed, and they are more graphitic. Okay, this is simply because the second step pyrolysis has removed the volatile components. If you look into the chemical composition, we can see that the nitrogen and oxygen level, the content after second pyrolysis has reduced. Most of it has reduced. So because of, as mentioned, it removed the volatiles, but the Fe still remain as it's not removed at that temperature, and thus it's slightly higher. If you now look into the active sites on this kind of catalyst, we have, in general consensus, the iron, the Fen moiety, they are responsible to be the active sites for the OR activity in the acidic, in this condition, in the fuel cell, hydrogen fuel cell environment. But from these results obtained from the XPS study, but in XPS, the disadvantage is that the iron, it has a low attenuation length, and also it has a broad range. So the results that we got on the iron spectrum may not be so accurate. So we're actually not able to determine the Fen moiety in exact. But we know that the nitrogen bonding environment in the structure itself, it plays a key role in determining the active sites. This could be contributed to active sites in the sample FENC catalyst as well. Okay, that's why we examine on the nitrogen bonding environmental itself. Here, if you compare the 4 types of the catalyst, the Fe-pennyl, penny is actually a polymeric type of precursors, hence the nitrogen content is relatively high as compared to others. Okay, you can see that for this penny, the pyridinic and graphitic pyrolytic nitrogen content are very high, and followed by the Fe ammonia. But upon second pyrolysis, as mentioned, the nitrogen content has greatly reduced, especially on 3 other samples, except that for penny, the atomic content is still quite high for it. And also there is a reduction in the pyrolytic end, but there's a maintaining in the pyrolytic and graphitic end, okay, itself. But the rest, they actually drop. Now, if we now move on to the OR analysis, while the cyclic voltammetry, we examine the activity, the OR activity for first pyrolyzed and second pyrolyzed sample. You can see that here, this is basically the OR peak, the oxygen reduction peak potential. Okay, so for urea, after second pyrolysis, it doesn't show any improvement. For choline chloride, yes, it shows some improvement, but mainly these peaks belongs to the Fe peak, and this reduction potential is pretty low here. While for Fe-penny, with first pyrolysis, it shows inactivity, but upon second pyrolysis, it shows a very apparent reduction peak here and very high current density obtained. While ammonia-wise, there's not much changes, okay, in comparing first and second pyrolysis. Now we move on to the linear sweat voltammetry analysis. How we determine the activity of the ORR of a catalyst is based on this point, the onset potential. The higher the onset potential, the more positive is the onset potential. That means the more active it is. So the PT is still, inevitably, is still higher as compared to the rest. Okay, so for first step pyrolysis, ammonia shows to be showing the highest activity compared to the rest. And here, this watermogram, it goes down without reaching a limiting plateau like this, saying it shows that on this catalyst itself, even though it shows good activity, but the active sites on this catalyst is not uniform. Okay, but we see, and also we can see that for Fe-penny, it's inactive, similar to the cyclic voltammetric analysis. Upon second pyrolysis, we see a drastic change in terms of the activity for the Fe-penny. You can see from here, now it is actually the Fe-penny which shows to be the most active as compared to the rest. Of course, it's still slightly lower than PTC. But interestingly, we can see that the current density of the Fe-penny that obtained is almost twice of that of the PTC, showing that this catalyst, and also at the same time, as you can see from here, it shows a limiting plateau, showing that it shows a uniform active sites distribution on the catalyst itself, okay, which is a desired property of the catalyst. Okay, so but ammonia-wise is still quite similar, but it's approaching a limiting plateau, a better limiting plateau as compared to the first pyrolysis, showing a better performance. Okay, now if you compare the results, this Fe penny RGO after second pyrolysis with the Fe penny RGO produced from the graphite. This is the result produced from the graphite. You can see that the activity is rather low as compared to this produced from the biomass, simply because of maybe of the speculation on the role of the impurities and also the defective sites that's actually contributed, okay, that has contributed to the activity, and also helps to this high current density of this penny helps to increase the fast electron transport, okay, and that possibly can lead to a promising performance in the single cell. And then we study on the effect of temperature towards the OR activity on this selected catalyst, the most active catalyst. You can see that with increase in the cell temperature, we tested for OR. Just for information, OR is tested in a half cell. Okay, that means we only do a 3 electrode cell system and only test on its activity towards oxygen reduction reaction, not in the single fuel cell yet. So in this half cell test, when we manipulate the cell temperature, with increase in temperature, we can see that the onset potential, the potential here, shift to the positive direction, showing that at a higher temperature, the kinetic of the catalyst is better, which you can see from here, the taper slope, okay, from this taper plot, that these from low temperature to high temperature, there's a reducing in this taper slope. The ideal value that is comparable to the PTC is at 60 millivolt per decade. So at this 80 degrees Celsius is near to the desired value. On the aspect of durability, chronoamperometry study was performed, and it was showed that on the Fe-penny RGO, it retained about 90% of the current after 16,000 seconds study in the same environment. It is more superior compared to the PTC that actually degrade faster in terms of the current density. And lastly, we study on the single cell performance in the PEMFC. We can find that unfortunately for this Fe-penny RGO, we find that the highest power density was just about 1.3 milliwatt per cm square, while for the PTC, it can achieve 60 milliwatt per cm square tested in our laboratory. Okay, so why is that so? Despite that, it shows a good activity, OR activity in half cell, but not in the single cell. So we speculate that the lower single cell performance of the Fe-penny RGO catalyst used in the PMFC is originated from the issues with the highly hydrophilic surface of the FEN RGO. That can lead to water flooding, because we know the products from the product from the electrochemical process is water. Since the surface of this catalyst is hydrophilic, so water tends to adsorb on the surface. Once it adsorbs on the surface, it will block the active sites of the surface for the next batch of reaction. Okay, so this is one reason of one issue in the FENC catalyst that has to be further studied, probably in terms of how do we increase improve the water management on this layer. For example, how to incorporate the hydrophobic agent on the surface, as well as how we can tune the pore size of this catalyst layer in order to facilitate the transfer of this water itself after. So comes to a conclusion, fuel cell technology is the future technology for clean energy generation and one of the clues to exercise low or zero carbon city. The ultimate low and or zero carbon technology in transportation is definitely the use of fuel cell. Okay, and we can use renewable energy mix to produce green hydrogen as fuel. The development of catalysts is crucial in reducing the overall manufacturing cost of PEMFC to realize the commercialization. Extensive efforts are made on finding PT-free catalysts as replacement. Among all, FENC is one of the promising candidates. Solution to flooding issues on hydrophilic catalysts during the fuel cell operations is sought after to make it feasible to be used. Okay, so that is all for my presentation. Before I end, I would like to introduce to you the online training course that is organized by our institute in the end of this month. If anyone is interested, you can contact me. Okay, thank you very much for your attention.
Thank you, ma'am. Your lecture was very informative. Now, all the participants are requested to join with respective track.
Anusha, first open for questions. Anusha, 1 minute. Questions post. Any open for discussion. Participants can have any. If you have any clarification, you can ask. Open for question session.
Thank you, ma'am. Very informative.
If there is any questions, you can ask participants. Fine, ma'am. Thanks a lot. In the absence of any questions, we once again, on behalf of the SVC management, principal, HOD chemical and HOD chemistry, I thank you once again. I request our HOD chemistry to share a few words.
Thank you very much.
Thank you.
Very nice presentation and a lot of information about the development of the catalyst. What are the various techniques utilized for the used for the characterization, and what are the recent developments of various catalysts which are used for this fuel cell application. Everything you have given an input. So this will give an insight into our current researchers. So to further strengthen their area, and they can think of developing some innovative catalysts which are cheaper and will have superior catalytic activity.
Another track in the fuel cell வேற இருக்கு இன்னொரு டிவைஸ்ல இந்த 1 minute.
Nachipan sir, please.
Nachipan, please view. Thank you, ma'am. Thank you very much.
Okay, thank you very much, everyone, for giving me this opportunity.
Thank you.
Thank you.
Thanks for accepting our invitation.
Yeah,
thank you.
Ma'am, 1 minute. Nachipan.
Nachipan, கேளுங்க.
Tell me, Nachipan.
Nachipan.
Okay. Dr. Rajesh.
1 minute, சொன்னீங்க.
Yes, sir.
You want to share any information with us or madam?
Dr. Venkateswara, thanks for accepting the invitation. We have called you just 2 or 3 days before only. Immediately you have accepted our invitation, and thanks to be a part of the international conference on clean materials and renewable energy and joining with us this time. Thank you very much. Thanks a lot.
Thank you. Thank you for the invitation. See you again.
Ma'am, Nachipan, applied assistant professor in applied chemistry department. So more than 10 years research experience in hydrogen-based PEM fuel cells. So it developed in 1 kilowatt to 10 kilowatt PEM fuel cell based UPS under government projects for DST.
Oh, I see.
Yeah. So various models, so 10 watts to 10 kilowatt fuel cell, hydrogen based fuel cells, sense of platinum catalyst. The membrane is an Appian membrane. It's already developed in the SPIC Science Foundation, the same management. I'm working in the SPIC group. Now currently I'm working the assistant professor in Venkateswara College of Engineering Then now I concentrate in research testing part in hydrogen-based PEM fuel cells.
On the system itself?
Yes.
Focusing on the system.
Yeah, system.
Right. So the project has been completed, sir.
Achipan, you can interact with madam and you can get inputs, and
sure.
you can have some collaborative work also, so that we'll have tie up with madam's collaborative project work with our SVC Institute. So
that would be interesting.
This international conference is as a enough for sharing the ideas, so that further developments can be done in the form of a collaborative one. So thank you very much.
Sure, sir.
Okay, thank you.
Be in touch with madam's contact, so we can also develop here further.
Thank you, ma'am.
Over to Anusha.
Okay. Thank you, everybody. Now, all the participants are requested to join in their respective tracks.
The participants are requested to join their respective tracks. We can start the presentations there. Will be taken care by the chair and co-chair.
Okay, we'll leave the link and we'll join that. Thank you.